Section: Introduction. In this section, we discuss how reinforcement learning algorithms typically require a large number of trajectories to learn a task, which can be time-consuming, especially with complex simulators. Model-based reinforcement learning, MBRL, comes in handy here. With MBRL, the agent learns how the environment behaves by understanding how its state changes with different actions. This method is more efficient because the agent can train in its mind without needing direct interaction with a simulator or the real environment. Moreover, the learned model enables the agent to make safe and accurate decisions by using different planning algorithms to decide its actions. Most MBRL methods follow a structured three-step approach. 1. Representation learning, where the agent simplifies the high-dimensional environment state into a more manageable form. 2. Dynamics and reward learning, where the agent learns how the environment changes and predicts the next state and associated rewards. And 3. Policy learning, where the agent figures out the best actions to achieve its goals. Dreamer is a group of MBRL agents that follow a similar three-step approach. Dreamer v1 used a specific model to learn about the world. Dreamer v2, an improved version, is more efficient and scalable by including a discrete latent space for modeling dynamics. Building on this, Dreamer v3 incorporates SimLog predictions and various techniques to stabilize learning across different environments. Dreamer v3 outperforms past models across various tasks while using fixed parameters. However, Dreamer models are not very sample efficient. Training them can take an impractical amount of time, ranging from months to thousands of years, due to inaccuracies in the learned world model. These inaccuracies lead to errors in decision-making, especially in complex scenarios. To address this, recent works have started using transformers, which are effective in capturing long-range dependencies in tasks like natural language processing and computer vision. TransDreamer was the first to use a transformer-based world model, outperforming previous models in tasks requiring long-term dependencies. MWM and TWM also use transformers for better performance in different tasks. On the other hand, Iris faces challenges in policy learning due to using reconstructed images. In contrast, our approach, DART, uses transformers for both world modeling and policy learning. We focus on fine details for precise decision-making and introduce a memory mechanism for better performance in partially observable environments. Our model achieves top results on the Atari 100K benchmark, showcasing superhuman performance in several games. Section Summary. In this section, we introduce a novel approach called DART that leverages transformers for both world modeling and policy learning. By utilizing a transformer decoder for world modeling and a transformer encoder for policy learning, we improve upon previous methods like Iris, which relied on CNN and LSTM for policy learning. Our discrete representations capture abstract features, allowing the model to focus on task-specific details, resulting in enhanced decision-making and achieving state-of-the-art results on the Atari 100K benchmark with superhuman performance in 9 out of 26 games. Section: Method. In this section, we present our model, DART, which is designed to excel at playing Atari games by operating within a partially observable Markov decision process, POMDP, framework. The POMDP is defined by a tuple consisting of the observation space, O, action space, A, transition dynamics, reward function, discount factor, and episode termination indicator. Our aim is to determine a policy, pi, that maximizes the expected sum of discounted rewards over time. Our training approach, inspired by Iris, involves 3 main steps: representation learning, world model learning, and policy learning. In representation learning, we leverage discrete symbols to model the observation space, similar to how human languages use discrete symbols for communication. We employ a method called VQV to discretize the observation space, allowing us to capture detailed information in the input image as a set of discrete codes. Moving on to world model learning, we use the discrete latent representation to predict future states, rewards, and episode terminations using a transformer decoder based on the GPT architecture. This training is done in a self-supervised manner, where the model learns to predict the next state and termination using cross-entropy loss, and the reward using mean-squared error. In policy learning, the policy is trained within the world model using a transformer encoder architecture based on VIT. The policy processes the current observation as discrete tokens received from the world model, incorporating spatial information using positional encodings. The output is processed through multiple layers to generate the action and estimate the expected return. Overall, our approach focuses on discrete representation learning, autoregressive modeling of dynamics, and policy learning within the world model to excel at playing Atari games effectively. Section Summary. In this section, we introduce our model, DART, designed for mastering Atari games within a partially observable Markov decision process, POMDP, framework. Our approach involves three main steps: representation learning using VQVAE for discretizing observation space, world model learning employing GPT for dynamics modeling, and policy learning with VIT for decision making. By discretizing observations and leveraging autoregressive modeling, our approach enables effective memory modeling without the need for recurrent networks, enhancing performance in Atari games. Section: Experiments. In this section, we assessed our model's performance using the Atari 100K benchmark, which includes 26 games that test perception, planning, and control skills. We measured our model against existing baselines using metrics like human normalized score, superhuman score, interquartile mean, IQM, score, and optimality gap. Our model received RGB observations of 64 × 64 dimensions in Atari environments, with a discrete action space, and was trained using 100K environment steps. The world model was trained with a causal transformer, while the policy was trained using an encoder transformer, allowing for faster computation compared to previous methods. Our model, called DART, showed strong performance in comparison to other models, with higher median and IQM scores. It outperformed the previous best model, Iris, in 18 out of 26 games, achieving a superhuman score in 9 games. We also analyzed the attention maps of our transformer policy, showing how information aggregation through self-attention varied based on the task requirements in different games. DART excelled in games with many approaching enemies and complex tasks, while Dreamer v3 performed better in games with simpler components and global information sufficed for planning actions. Section Summary. In this section, we evaluated our model using the Atari 100K benchmark, assessing its performance based on various metrics like human normalized scores, superhuman scores, interquartile mean, IQM, scores, and optimality gap. Our model, DART, trained with a GPT-style causal transformer for the world model and a VIT-style transformer for the policy, outperformed other models consistently in terms of median and IQM scores across all 26 games. Additionally, DART demonstrated adaptability in different game environments by focusing attention on relevant task-related details, showing improved performance in tasks with multiple components compared to previous models like Dreamer v3. Section: Ablation Studies. In this section, we examine DART performance in various experimental setups across 5 different games. The first scenario we looked at was DART's performance without positional encoding. We noticed that in games like Boxing and Kung Fu Master, where the agent needs to interact closely with its surroundings, omitting positional encoding significantly affected performance. However, in games like Amidar, where the enemy is not always nearby, the drop in performance without positional encoding was minimal. Transformers inherently consider the overall context but need positional information for precise decision-making. Adding learnable positional encoding boosted performance significantly. Next, we explored DART's performance without random exploration, relying only on agent-predicted actions. However, like in Iris, our model faced the challenge of declining performance without new environment states introduced through random exploration. For games with simpler dynamics like Sequest, the impact was not as significant. We also studied the impact of masking memory tokens, which affects the proper modeling of memory crucial in reinforcement learning. Aggregating memory over time improved DART's overall performance, but the effect varied in Atari games with diverse dynamics. In some games, decisions were based only on the current time step, making memory tokens unnecessary. However, in games like Breakout, Private Eye, and Krull, tracking memory was crucial for optimal planning. Furthermore, we analyzed the consequences of randomly masking observation tokens, selectively removing low-level information. This had a noticeable impact on the agent's final performance, especially when masking all observation tokens, leading to a significant drop in performance as the agent focused solely on memory tokens. Moving on to related work, enhancing sample efficiency in reinforcement learning is a fundamental challenge. Various approaches have been proposed to accelerate the learning process, such as model-based reinforcement learning, uncertainty estimation, and using complex model architectures like transformers. Learning low-dimensional representations of the environment, such as through variational autoencoders, VAEs, can also improve sample efficiency by capturing informative representations of the input data. Disentangling representations have shown to help in modeling interpretable policies and enhancing learning speed on manipulation tasks. Recent works have utilized VQVAE for learning independent latent representations of low-level features, leading to robust and generalizable policies across different tasks.